Hello everyone who is watching this video. This video is about my mini project which is part of my completion for the MTech program in IIT Jammu. The mini project which was given to me was about a phaser management unit. Basically I was supposed to design a machine which can accurately find out the correctness of the data which is received from the PMU. PMU is a device which is located at each node from where the distribution system relays the electricity to the consumers, and then over those there is a device called PDC, which is called phaser data concentrator. This basically takes the data from all the PMUs, and at this stage in PDC we verify whether the data which is received by the PDC is correct or not. So the project title basically involves detection, basically making techniques so that the cyber faults or the cyber attacks can be found out, or if there is any other kind of fault which is coming in the data stream from the PMU should be visible to us using the algorithm and techniques that we are using in the project. Now I'll walk you through the complete development stages of my project. I'll take you to my project directory, and from there we'll begin this. This project started around 1.5 months ago, and initially we started with a basic waveform generator which actually multiplied to multiple PMU simulators working at once. But finally we settled down to a single PMU simulator which will give us 3 PMU outputs of single phase, of one phase itself, and we'll be running comparison algorithms across those 3 phases. And for that PMU simulator, this was the first fully working iteration that I made, and I think this file should have a timestamp as well. So this file was completed on, probably this is the modified date, I think the file was created before that, but on 10th of August I guess the final version of this file was complete and shared. I'll run this file here, and I will show you the output waveform and what kind of output gets saved with this. So this is the waveform which comes in the output. This particular PMU simulator has 3 waveforms in output. It has a simple sinusoid wave output which is Im sin omega t, then we have Im sin omega t plus phi, and then we have Im sin omega t plus e raised to the power minus t by tau. So these 3, which is a DC decaying component in the third section, and we can see the function of this DC decaying function, DC decaying function which we added to the sine wave in this plot itself. In the start you can see the DFT window, the middle one, actually shows the higher magnitude when the signal starts, and the phase difference in the current, you can see it is aptly visible here. It is quite pronounced, and as the signal processes, as the time progresses, we can see the magnitude of my decaying DC component slowly reducing over the period of time, and eventually it fully fades away as the signal progresses. And the window can be modified for generation of the signal, for this generation of the signal, and I think I have put a 10-second window for this. So this generation of waveform is going to take a lot of time because I am printing each and every sample here. So that's a huge load on my CPU. As you can see, the temperature over here is already 101 degrees Celsius, so the computer is currently running at max. I solved this problem using a bigger window, a bigger time frame, which I will show you in a couple of minutes as we progress further into the project. I'll open this file for you so that you can see how the template was prepared and the three functions which get generated. Sorry for the background noise. There are a lot of vendors which visit my house, and especially when I'm presenting something. So in this file you can see the three different waveforms. This is the simple Im sin omega t, the first waveform, the second one with a time delay, and third with a DC decaying component. These three waveforms were selected for the demonstration, and in the end a CSV file gets generated, and in the CSV file we get these headers. This was our primary what I can say waveform generator without any fault. We did not induce any fault apart from the three standard waveforms which we added here. And why the three waveforms are not ideal waveforms, that is 120 degree separated waveform, because usually what happens in the real scenario, we have different kind of loads which are constantly running in the supply, and these capacitive or inductive loads induce some kind of transients in the circuit. So for that reason we injected a transient from our side in the third waveform itself, and the second waveform, which actually increases time by a certain fixed ratio, also points to the same direction. So this was our basic setup. From here we added more faults to the signal as and when we progress in the project. I'll take you to that part of the project as well. Let me open the project window. Where did it not open or what? So this was my first directory under the DSSE PMU. I started the work. Later on, when the project became more complex, I actually made an internal directory and the entire project went inside it. There you can see this was my final generator which I am using for the project now. This has much more options and much more control over the waveform. Using this template, I can generate different kind of faults in different formats, in different combinations. The faults which are labeled here, you can normally see here. This is for the normal measurement. I can basically induce a constant sync error. Then I can induce a measurement noise, which we'll see just now. A couple of minutes. I'll just show you in the waveform once more when I start the GUI. Then we can induce packet loss. We can induce bad data. We can induce sync fault. We can set the parameters of sync fault. We can induce the clock drift, and we can set the parameters of clock drift as well. And then there are certain offsets also, fixed offsets that we can induce in the waveform depending on the injection of faults which we want to measure at the PMU fault simulator. I mean at the PMU fault measurement side. I'll run this file and show you the difference in the original version and the version which we are now using for the project. So here you can see the time is progressing pretty fast. It is almost equivalent to the clock that we are using. It is a 10-second display window, and it will complete in exactly 10 seconds. So 10-second window is complete, and we have induced multiple faults here, and this simulator generates both current and voltage magnitude, and DFT and the phase. We can scroll this window to see our entire signal range. You can see the fault sections here. You can pinpoint, zoom in, and see how exactly the things are changing when the faults were induced. The difference in phase, difference in the magnitude. You can zoom in on the waveform to see the noise which we have added. This way we are actually able to debug and control our project much better. So this GUI helped us quite a lot. And apart from that, a CSV is generated carrying all the details. So here you can see PMU output.csv gets generated, and this file contains the data. I can show you the CSV here in the VS Code itself. Yeah. So the file is here. Next we will go on to the project structure, and I will walk you through the PMU detection side. This was the generator, the output which we are getting from a phase management unit or phasor management unit. Now this data is ported to a phasor data concentrator, where this information that is being sent by the PMU gets evaluated. This was our actual project. In the absence of an actual three-phase supply data from an actual PMU, I had to make a PMU simulator also that generates the dataset for me, and then once the PMU simulator was generated, only then I could actually make a fault detector for it. So now we'll move on to the fault detection side of my project. Now I'll walk you through the fault detection side of the code. The fault detection side of the code involves these files. Starting from the top, there is this file called gsquare.py, there is jacobian.py, there is loadprofiles.py, then there is main.py, measurement loader.py, although we are not using this file in the project now because the topology changed. Then we have measurement model.py. This is the most important part, wherein we actually convert this complete setup into a three-phase mode, and we introduce the admittance formula here. Then we have network model.py. These two basically, measurement model.py and network model.py, both of these implement in synchronization this particular concept of admittance, and finally impedance Z that we calculate in the program. Eventually then we have this neural active fault controller.py. This is the main program that controls the activity of our neural engine. This neural engine involves machine learning API from Python that we utilize, and I'll tell you about that MLP API of the Python as well. Then once these three files are done, I mean neural fault management demo.py, this is a controller for the complete setup. I mean we have to call this file so that the both algorithms, the neural controller and the traditional physics controller, run properly, successively in a particularly defined fashion. Then we have a neural fault training pipeline. This trains my MLP engine using the data sets which I downloaded from internet also, and the ones which I generate from my PMU simulator also. I can use both the data sets for training my model. Then these CSV files we already know about. We generated it using our waveform generator or PMU output generator. Then we have yes, these were my simulator PMU simulator Python files. Run fault cases.py. This file I particularly prepared for running multiple test cases at once, so that I don't have to write commands for running each and every case. I can add the cases here and different configurations of my PMU simulator. It will generate the data, then it will train the data, train my simulator using the data set, and then finally fetch the result from me, all done automatically. Then we have state estimator.py. This particular file is used for estimating the state. I mean, there's a state matrix in the project which I showed you during the presentation. It's a 12 by 12 matrix wherein we are using 6DOF only, and so that 6DOF matrix generates a state vector for each particular frame that we input to the PMU detector. So 20 samples per frame, so 20 vectors are generated for each state, I mean for each time stamp that we have, or each unit time that we have according to the sampling rate of 1 kilohertz. Then we have WLS.py. This implements the weighted least square algorithm as and when required during the complete project flow. So this project is actually modular. Each mathematical concept is implemented as an individual file. As you can see in the top, we have chi-square.py. So wherever the calculation of chi-square is required, we simply call the functions defined inside this file. Internally, if I describe each and every function, it will become pretty huge and boring for all of us. The project is already there on GitHub. You can go and check it out yourself. Then we have WLS.py. It implements the weighted least square formula. Then inside the measurement model.py, there's a small description which is put there in the top itself. It basically explains what exactly it is implementing inside the matrix and how the data gets populated. So most of it is self-explanatory. I mean, the formulas itself are pretty basic. We are not doing anything very complex here. It's a 3 phase PMU simulator only, but the data churning concepts are rigorous that we are implementing. The design is simple because we are not having hundreds of PMUs like we have in a real PMU-DSSE-PDC setup. Here, for demonstrating the proof of concept, we are only using 3 waveforms. Though the algorithm which we are implementing on these 3 waveforms are real and they do deliver the results the way it should deliver in a real PMU setup itself. So the only part which is remaining is the scaling this particular setup to a higher order, wherein we have more PMUs, more input data, and a real report generation algorithm will also be needed so that it is properly displayed to the people who are operating on it. But this particular setup properly gives us a proof of concept about working of a PMU-DSSE-PDC setup. I'm just checking if I missed any other file which I should explain before we move on with further operation of this API. Mail.py is the file where basically it sequences the complete project. What is going to happen when? We can simply start from the top itself because Python is a dynamically typed language. Everything happens in a sequence. So it's a top-down way of programming our complete project, wherein we simply have to go from top to down to understand the flow of our implementation. Compared to other languages, wherein a complete project can be divided into a number of files and the flow can be in a random organized way. Here it is not the case. If I open a file, it is always in a top-down fashion. So my program starts from this particular line, valid measurement rows. It's a function. It basically checks whether my rows are valid or not. So some checks are put in the function definition that checks whether the data which is there inside that particular row of my CSV is a valid value or an invalid value. And there are some predefined functions inside the Python library which does the job. Then we have a truth defining truth defining function. It checks the output of my statistical calculations at different stages, and it gives us a truth index, whether the output value is a true value or not, by checking out the matrix organization which I shared during my presentation on Sunday. So these functions are implemented. If I go function by function, it will become pretty huge for us to understand this complete whole project. But for a person who is interested in understanding this complete implementation, he can simply follow a top-down approach. He can go function by function, checking what exactly each function is doing. He can simply press Control and go inside the function, and what exactly is this doing inside the function gets listed out. And most of it is logical and self-explanatory. So in this demonstration, next thing that I wanted to explain was the neural layer in the project. As I already explained in the beginning, that the project is now divided into two branches. The one is the original DSSE PMU branch, and the new one is the neural branch. So before we move on to the neural branch, I would like to show you what I did in the original branch before migrating to the final DSSE PMU neural branch, which implements the actual neural layer in the project. So let's go back to the project directory. This is the branch which we are presently discussing. I think in my previous discussion about the PMU simulator, I forgot to mention about one file, which is loadprofiles.py. Loadprofiles.py is used to simulate various kind of loads in the power supply. These loads, I have assumed that we are making it for a power supply system, but this model can be implemented in any other kind of circuit as well. We can use the same model for designing a feedback system for 3-phase inverter motor. I can scale this model up from 3 phases to 6 phases, and then I can use a 6-pole motor or a 6-phase inverter motor, and use the same feedback system which I have made here of fault detection for the speed and torque correction of the motor. Similarly, I can use it for other applications of electronic circuits. Not only motors, I can use it for many other kind of diverse circuits which utilize multi-phase power inputs or multi-phase what I can say synchronization inputs for making the circuit run. So this project actually serves as a template for such kind of implementations. In this I simulated multiple kind of loads in my PMU simulator. I can basically select a load profile and output it in my waveform, and then use my fault detector to see whether it is properly detecting the faults or the load profiles in the detection section. So there is motor starting, that is inductive load, capacitor switching is capacitive load, EV charging is heavy resistive load, load shedding is uneven. So there are different kind of loads which we simulated here with lead and lag values. Let's move on to the neural section quickly. So I tried to make a small MLP API here. The idea was to set the thresholds for detecting the faults using only the data set, and by simply learning from the faults which have happened before in the history of operation. This is done basically from taking into cognizance a large data set which wasn't there for me, So I use the simulator to generate it, and then from that huge data set I will try to find out maxima and minima for each fault, and then I will actually try to put pointers that suppose if this much maxima happened or this minima happened, then what is the fault that actually caused this type of maxima and minima. So for example, a particular maxima happened at 9 amperes and with certain degree of phase shift, say for example plus 10 degree or plus 20 degree, and this particular combination is more prevalent when a synchronization fault happens or a bad magnitude fault happens in my power line. So I'll tag it as I'll assign a kind of weight, a probabilistic weight, that okay, if this kind of combination happens, then there is 90% chances or 95% chances that this is going to be a magnitude based fault from the bad PMU. So that way I basically develop a kind of model which saves these occurrences, what we call outliers, in a separate vector, and then we use this information to accurately predict what's happening in my PMU in real time when it is running. So that was the entire idea, that we are using the actual statistical techniques which calculates the weighted least squares and runs a chi-square approximation algorithm to narrow down the fault. Then we we make sure that the deduction that we have done from the statistical technique is correct. We actually added one more layer of neural inferencing that actually solidifies our output whether the detection is correct or not. So now we have two layers that in fact verifies our final output in the device, which kind of fault we have encountered. So I'll reiterate again, the idea was to first find the fault, any fault. I mean, if there is an anomaly in the circuit, it will be recorded. If there is a sudden change in the phase, it will be recorded. If there is a gradual shift in the phase, even that will be recorded. So all kind of anomalies that happens when the ideal waveform is not present. We have provided an ideal base scenario, that suppose this is my base scenario, if any deviation from this base scenario happens, then please record that scenario. So we get all those faults, but we still don't know what kind of fault it is. Now for finding out the faults, we use two techniques, again the WLS plus chi-square, and for solidifying our outputs we use the neural inferencing. So then both of these techniques, they complement each other in landing us the final correct output. So I tried to implement it, but the code was becoming very long. So what I did, instead of making a custom MLP for this specific task, because it's a POC project, so what I did, I used the inbuilt MLP API which is provided by the Python, which reduced a lot of repetitive code for me, because MLP is already implemented. I mean, when the entire code construct is already present, there is no point of me repeating the task again for this project, until and unless it is saving my time or I am implementing it in some different fashion, which I am not. I am using the same exact concept which I just explained to you, and when the construct is already present in Python, so I simply picked up that function from Python and implemented it. So that implementation is not in this code base. I shifted my project to a different directory, and we will move on to that explanation from here. Continuing my description, we actually saw the neural implementation which I tried doing in my previous project directory. Now I will show you the present incumbent directory that runs our current code, from which I have pasted the output waveforms in the project report which I have submitted with the map. Let me open that here. So this is the project directory that is presently running the output. This is the project folder from which I have generated the output screenshots, which are pasted in my final submission report. I'll quickly move on to the neural part, because other things are exactly same as the previous directory which I have already explained. Here I'll directly go inside my neural controller, and the most important part which I should actually show here is the training part. Train multitask controller v4.2. Yeah, multiple iterations happen, so now it is v4_2. In this I simply call the main MLP function from the Python library. We can see how it actually implements the MLP. It classifies the data, and then it is fed inside the MLP pipeline. So these are predefined functions inside the MLP. It is calling a pipeline function, and pipeline I am passing the scalar values and the classifications constants, or what you call it, the coefficients, using this function called MP classifier. We can go inside this function and see what exactly it is doing. So it is implementing. We can simply check out the code here. So this is _multiply_perception Python file which is inside the library. It is not entirely accessible to me. And similarly, standard scalar is the function. This is the formula which it implements. So in this way, I simply ported my data to the MLP API of the Python, and it gives me the churned out, it churns the data, and it deciphers the data. It decomposes, finds out the output for us by running in the, so this is the trainer model, so it basically takes in the data and it saves all the thresholds by running a constant loop and assigning the probabilistic weights to each kind of fault that we have provided. The classification we have already provided, that and under what kind of different faults we have to classify the data. So that information is already fed to the MLP using these functions, and eventually it assigns those probabilities and what I can say attachments or the linked frame for the faults versus data set. The set of data that we have. It implements, I don't have exact vocabulary to basically explain this phenomena, but we can simply say that we are linking the data to the probabilities of actual happening, actual fault. So that particular task is taken up by this training module, and then we take the data from neural active fault controller. This is the file which gets created once I run this training model, which I'll show you in a couple of minutes once we are done viewing these Python files. So the evaluation happens here. Here we detect the cases. In this file we detect the cases from both the parallel paths that we have. We have WLS plus G square statistical path. That is also called here, and the calculated output is presented here for comparison. Similarly, from the neural pathway also the data gets accumulated here, it's called here and compared for the final output. That function here is generate windows, select this window. The final function is run cases. Yes, in this you can see when we run the cases, we basically assign what kind of fault type it is. The neural result is classified under fault type, then faulty PMU, and what is the confidence level of the deduction that we have made for the fault type and faulty PMU. WLS gets calculated here. Then decision matrix happens here. The decision matrix I have already presented in the presentation. There is a decision matrix which is there. I can basically show it to you right now also. Let me show it so that there is no confusion. this is a decision matrix. So if everything is normal, the weights assigned is 1.0, 1.0, 1.0, 1.0 for magnitude and phase of both voltage and current. If it is a bad data, then the assigned weights are 0.1, 0.1, 0.1, 0.1. If it is clock drift, then it is this, and if it is a synchronization problem, then it amounts to this. So that is how we basically decipher what kind of fault it is. And then there is an internal weights assignment that happens, which associates it with the accuracy part. That is how we are able to predict display a accuracy figure, that what we have inference from our model is, how much are we confident that the output is going to be this. In reality, we don't have the actual situations, what exactly is happening at the PMU end, because it is in a remote location. We only have the data set, and so we have to attach a probability that, okay, this is what my assumption is, this is what my algorithm says, that it is 61.53% chance that it is a sync or drift kind of error, and there is this 72.41% chance that it is a bad data or timing gate error. This kind of model has been implemented, and this accuracy actually improves with the data set that we actually input for training the model. If we provide a very huge database with almost every kind of fault outlined in that, the accuracy figure substantially improves here, because I am able to get a 96.9% normal fault gate figure and 99.38% for faulty PMU, because that part is trained most for this particular project. This is the part on which I spent most of my time, because this was the core area of the project. First, we were supposed to detect whether there is a fault in the incoming data from PMU or not. That is why I am seeing a 99.38% accuracy in this. While the least amount of time was spent on sync drift specialist. Specialist is a different. There should be one more line in this table. I forgot to implement that print. Actually, there are two levels for deciphering the fault when it is a sync or drift fault. First, it is a normal implementation, and then I implemented a specialist code for it, which further divides the data into windows for understanding whether it is a synchronization fault or it is a drift fault. A drift happens when we have a continuous change in phase, and that is periodic, plus it is changing by a specific delta. For example, the phase is changing by 0.05 degree after every few seconds, say after every 10 milliseconds. It is changing by some fixed angle. Then it is a kind of phase shift that we are experiencing, and for what amount of time this happens, and whether the waveform is again gaining the phase back or it stays there. So such kind of classification and differentiation is present inside the specialist model. And before specialist model, there is a basic differentiation. If it is a drift, that means there will be a constant change in the phase with certain fixed angle. While synchronization fault happens when, suppose if the two PMUs which are sending the data, they send us the data with different timestamps. The PMUs kept the timestamp same, but the data was actually received for a time which is either from the past or the future of the present time. So that is a synchronization fault. While in the case of drift, we are not experiencing any timestamp related issues. In case of drift, our data is basically our phase is actually getting shifted by a fixed angle with every iteration. So these were the two faults which are supposed to be found out and need to be deciphered because the detection algorithm is not able to differentiate between these two faults very easily, because they look similar to my model. So hence I had to find out extra classifications which can make me differentiate between a synchronization fault and a drift fault. So that this particular area is open to more refinement, and I have certain ideas which can be implemented to even more refine this particular model to have a better accuracy. And of course, with the increased dataset training, it will automatically improve. Let's go back to the project directory. So yes, this was the neural implementation. I have shown you the training part, and then I have shown you the detection part and the decision making matrix. And using this particular file, I take the input from the dataset which I created using my PMU simulator or the trained data, and I feed it for so first what happens is I have to train the data. When I run this particular file, train multitask controller v4 to final.py, then it takes this huge data which is present in the form of CSV, which represents different kind of faults, and it trains itself. And using this training, when I finally run my multitask active controller v4 to final.py, then it uses the data which is generated by my PMU simulator, which I am generating in real time, and then it tries to find out the fault in that data using the training which it has received from this training data or scenario data. So this was the this was the complete implementation of my project, and I will show you a demo run of both of my these directories. The first directory actually gives pure statistical output. I'll run that as well, and this model as well. My computer is doing some weird problems. So these are the kind of issues which I face sometimes. This is my latest run, which actually prints the output by running both algorithms, statistical algorithm and the neural algorithm. First I will show you the training part. For training I need to run the demo.sh. Now it is training the data. After training the data, it generates a file, a blob file. That blob file contains the training vectors, and from getting the information from those training vectors, it decides what kind of fault is present in our real-time data. It takes some time for training the data. You can see the temperature of my computer primary pulse has reached 101 degrees Celsius. That's the max. That's max for this laptop. I think this laptop won't survive for very long. So you can see the V4.2 model has been trained and saved. So once it completes running the simulation runs for the faults, I will show you where the new file is generated. So these were the 4 basic test cases which I ran with this script so that I know my my complete system is working. I'll run the more comprehensive 10 test scenario after this, after showing you the blob file which gets generated here. The camera failed again. Let's do it without the camera. No problem. So here I'll do ls-la so that you can see the timestamp. Here, this file you can see. I think I am inside the wrong folder. We need to go inside the neural controller because I trained the data in my neural controller. So yes, this is the file. Yeah, this one is the file which is generated right now for us. Neural active controller underscore b42.jobline. It is generated at 2:21 AM. I can see the time here in my clock is 2:22 AM. So this is the file which is generated, and same thing it says here also. This is the name of the file, neural underscore active underscore controller underscore b42.jobline. Same file is generated here. So this is generated by that MLP function which I just explained to you. So this is the output which it generates. Now when I run my inferencing model, it takes the information from this block file and gives us or throws us the output. Now I'll run the 10 scenario, the long version. Yes. It is run full 10 case fusion evaluation final. This complete run and the screenshots I have already shared in my report. So the screenshots for one complete run is already present inside the report, which I think you can refer and see. This table is also has been pasted inside the report. This is the completely working algorithm for the cyber resilient PMU detection. PMU anomaly detection, and I will show you the output for the older statistical technique as well. This is the output which is coming from the statistical run. These screenshots are also pasted in my report, so you can see there. This actually completes my demonstration of the project. Thank you for this.